Hello, calculus students. This lesson will be on two different rules of differentiation known as the product and quotient rules. To find the derivative of a product of functions, use the product rule, shown below. The word product means that we are multiplying two functions. So here's a differential operator. It identifies that x should be thought of as the independent variable, and we have a product of a function f and a second function g. In this video, I do not intend to show you the proof of the product rule, just to show you the result. To find this derivative, you find the derivative of the first function, f prime of x, multiply it by the second function undifferentiated, and then add the first function undifferentiated times the derivative of the second function. It's as if you write the same product twice, separated by addition, and you simply switch which function a derivative is on. Now, another notation for this. If I let u and v represent two different functions, and I find the derivative using prime notation, then the product rule states we will get u prime v plus uv prime. It turns out that this generalizes. If you have three functions u, v, w being multiplied and you find the derivative, you can think of this as a product of uv and w and apply the product rule. So with the derivative of uv times w plus uv times the derivative of w. And then to do this derivative of uv, you do the product rule again, which is u prime v plus uv prime, all of that times w, and then plus uvw prime. Now distribute the w, and notice the result. You write the product uvw three times added together, and then switch the prime from u to v to w. I find the derivative below in two different ways using the product rule for one of the methods. In this first case, I think of u being this x, and v being the x cubed minus 2, and we have a product because they're being multiplied. So I know the result will be u prime v plus uv prime. So I find the derivative of u. Well, u is just x, its derivative is 1, and then times the second, undifferentiated, and then plus u, which is just x, and then times the derivative of v. So the derivative of x cubed, use the power rule, and you get 3x squared, and then the derivative of minus 2 will be 0. Now simplifying, we get 1 times x cubed minus 2, so that's just x cubed minus 2, and then we have plus 3x cubed. Now these two terms are similar, so it can be added, giving us 4x cubed, and then minus 2. Okay, the second way. Instead of using the product rule, we can first prep the function for differentiation using other rules by distributing this x. Distributing the x, we get x to the fourth minus 2x. And I haven't differentiated yet, so I'll put this in brackets, and you can either keep the d dx in front, or we can switch to the lazier notation prime. And now this function is no longer a product. It's a difference of two different functions, so I can differentiate term by term. Differentiating x to the fourth, we use the power rule, and that gives us 4 times x cubed, and then minus. Now we differentiate 2x. 2x is a line with slope 2. Its derivative is simply that slope 2. So in this case, you could argue that the second method was the easier method, yet we do not get a contradiction by using a second method, the product rule, to arrive at an answer. Now there will be times where this second approach will not be possible, and we will need to use the product rule or this approach. We will see some examples of that later on in the course. Okay, next page. Find each derivative below in two different ways using the product rule for one of the methods. Notice these derivatives are all in pairs. First example. It's possible to think of 5 times x to the 7 as a product where u is the constant 5 and v is x to the 7. If that's the case, then using the product rule, I'd get u prime, the derivative of 5 by itself would be 0, times the second, plus the first 5, and then times the derivative of the second, which is 7x to the 6th. This is my u prime v plus uv prime. But of course, 0 times x to the 7 will just be 0, so that term will go away. So we get, in the end, 5 times 7 is 35x to the 6th. Notice that when you employ the product rule, when one of your factors is a constant, then the end result is exactly the same as the rule of when you differentiate a function times a constant. So the function is x to the 7 and the constant is 5. And the rule we learned earlier is the 5 just stays, and then you differentiate the function next to it, and then of course combine those into this 35x to the 6th. The product rule does not contradict this because this first term zeroes out. Now just to show variety, it's also possible to have split 5x to the 7th as 5x times x to the 6th, or some other way. 5x squared times x to the 5th, 5x cubed times x to the 4th, etc. But if I split it this way and think of my u and my v, then the derivative would be, we'd have u prime, so the derivative of 5x is 5, times the second, which is x to the 6th, then plus the first, which is 5x, and then times the derivative of v, which will be 6x to the 5th. So this gives us 5x to the 6th plus 30, and then the x times x to the 5th becomes x to the 6th as well. And you add these together because they are similar, and we get 35x to the 6th. Again, getting the same result. Now, of course, the product rule was never really necessary here, because again, we have a constant times a function. So we know that the derivative of this will be that constant, just times the derivative of x to the 7th, which using the power rule is, again, 7x to the 6th, and then we can now multiply the 5 and 7, and again get 35x to the 6th. Now, if I were doing this problem, I would certainly just do it this way, but we're showing right now is that we do not get a contradiction if I think of 5x to the 7th as a product of some form and then employ the product rule. Similarly here, we have now u is the independent variable. Let's get the derivative just using the power rule. So the 4 would drop down, the u would repeat, and then we would have 1 power less. So 4u cubed. But now let's use the product rule just to show another way that we might go about getting this derivative. So I'll think of u to the 4th as u squared times u squared, and then find the derivative using the product rule. You could also have factored u to the 4th as u times u cubed. Now since u is already being used as the independent variable, my letters I'll use will be w and v. So the derivative will be w prime v plus w v prime using the product rule. So we differentiate w with respect to u, think of u as the independent variable, and that gives us 2u, and then times v, which is just u squared, plus w is u squared, and then times v prime, which is just 2u. So we get 2u cubed plus another 2u cubed, confirming we get 4u cubed. Again, this is not the best way to go about doing this derivative, but it shows that the product rule produces a result that is expected, that I got much more easily just using the power rule from the start. And this third pair, here z is the independent variable now. I'll think of this as a u times a v. So the derivative of z with respect to z is just 1. So there's my u prime times the second, square root of z, plus the first, which is z, times the derivative of the square root of z, which is 1 over 2 square roots of z. By way of review, if you want to differentiate square root of z, and z is the independent variable, then you think of the radical as a 1/2 power, and then use the power rule. So the 1/2 drops to the front, z, and then 1 less than a half is negative a half. That negative power on z pushes the z to the denominator with a positive 1/2 power, and then the positive 1/2 power is interpreted as a square root. Differentiating square root of an independent variable is so common that some students simply memorize this result. Okay, so simplifying our answer up above, 1 times square root of z is square root of z, plus, and then we have z over 2z, and I'll put that to the 1/2. Now this z in the numerator is to the 1. And then recall that if you have a to a power divided by a to a different power, you can combine this into a to a new power, which is found by subtracting n from m. So I could take this further and say square root of z plus, I do 1 minus a half, which is a half. We also have an implied 1/2 coefficient, so this is 1/2 z to the 1/2, which of course is 1/2 of square root of z. And if I get a common denominator, multiply this first term by 2 over 2, so that our two denominators match. And then we add 2 root z plus 1 root z, that gives me 3 root z over 2. And this is a good final simplification of this derivative. Now, as an alternate approach, we can combine these two terms into a single power of z. Recall that if you have a to the m times a to the n, you can express this as a to a power that is the sum of m and n. So in this case, we have z times z to the 1/2. This first z has a 1 power on it, and then we want to differentiate this, but first I'm going to simplify the inside. So we're going to add the powers, 1 plus a half, that's 2 halves, plus a half, that's 3 halves. So we have z to the 3 halves is what we are differentiating ultimately. Now I am prepared to use the power rule. The 3 halves drops to the front, z, and then Our new power is 3 halves minus 1 is 3 halves minus 2 halves, which is 1 half again. And then, of course, that 1 half power just means square root of z. And when you multiply this fraction times this non-fraction will go to the numerator because you can think of it as being over 1, and then you simply multiply across. So we can say 3 root z all over 2. And again, we do not get a contradiction. I still contend that if I were doing this problem, I would do this approach and not use the product rule at all. But there will come a time when our functions require the product rule. We will not have another option to find the derivative. Okay, let's go to the next page. To find the derivative of a quotient of functions, quotient meaning a fraction or division of functions, use the quotient rule shown below. So we have the differential operator, identifying x as the independent variable. And then we have a numerator function and then a denominator function. Now division is not commutative, meaning f divided by g is not the same thing as g divided by f. So it matters which function is the numerator. And the result of the quotient rule, which I will not prove, is we get the derivative of the numerator times the denominator, undifferentiated, minus the numerator undifferentiated times the derivative of the denominator. And then we divide all of this by the denominator undifferentiated but squared. In lazier notation, if we have two functions u and v being divided, and you find the derivative, the result will be u prime v minus uv prime all over v squared. Let me rewrite the product rule to have a comparison discussion. U times v prime is u prime v plus uv prime. Now with a product, multiplication is commutative. U times v is the same thing as v times u. So it really doesn't matter which function u or v you think of as the first one. So this term could be written first, and this term written second. And this is fine as well. That's because addition is also commutative. So it really doesn't matter which of these terms you write first. Now with the quotient rule, division is not commutative. 4 divided by 2 and 2 divided by 4 do not yield the same result. So it matters the function that is in the numerator should be the function that's differentiated first. Furthermore, this subtraction means that this overall numerator is not commutative. So it's very important that the numerator function is what gets differentiated first. I've also seen a mnemonic for the quotient rule. Here's a mnemonic for helping you remember it. You have a high function and a low function, and the derivative is low d high minus high d low, all over low squared. This low stands for the v that's there, and this d high stands for the derivative of the numerator. And then minus the high, which is the u, times the d low, which stands for the derivative of the denominator. If it's helpful, you can sing this to yourself, low d high d low, over and over again until it sticks. Eventually, you do want to get to the point where the product rule and quotient rule are both memorized. Okay, find the derivative below in two different ways using the quotient rule for one of the methods. In this first case, let's go ahead and use the quotient rule. I think of this whole function right here as my u function. Denominator function is our v. So I begin with the derivative of the numerator. The numerator is two terms. They can be differentiated term by term. The derivative of 3x to the fifth is 15x to the fourth using the power rule, minus, and then the derivative of 2x is just 2. So all of this is my u prime, and then times v. And now we subtract, and we write down u undifferentiated times v prime. And the derivative of v using the power rule is 3x squared. And then all of this is over the denominator squared. Okay, now we have some algebra to do. There are a few ways you might go about simplifying this. I'll take the approach of distributing this x cubed through these parentheses and distributing this 3x squared through these parentheses. That gives me 15x to the 7 minus 2x cubed, then minus. Now here you have to be careful. I will also need to take this negative and distribute it across these parentheses. So we have 3x to the fifth times 3x squared and then times a negative, and we get negative 9x to the 7. Then we have 3x squared times negative 2x and then times this negative. That gives me positive 6x cubed. And this is all over. And then when you square x to a power already, you multiply those two powers. So you would have x to the sixth. Keeping in mind, a to the m power raised to the n power gives you a to the mn power. Okay, now notice we have two similar terms there and two similar terms here, so we can combine a few things. The orange terms combine to be 6x to the 7th, and the greens combine to be positive 4x cubed. and this is all over x to the 6th. From here, there's more simplifying we could do. I could factor out an x cubed from both these terms and simplify, or I could take this x to the 6th and split it up under the two fractions and simplify them separately. Let's do that second approach. And then simplifying, 7 minus 6 is 1, so we have just 6x to begin. 3 minus 6 is negative 3, so we have 4x to the minus 3, or in other words, 4 over x cubed. I think of it as 6 is a higher power than 3, so I do 6 minus 3 and get 3, but those excess x's are down here in the denominator. Okay, so we got our derivative using the quotient rule and then a bunch of algebra to simplify this. Now let's do this a different way. I can take this x cubed and from the very start, split it underneath the two terms of this numerator before I do any derivatives, giving me this function instead. I still need to differentiate it, so I'll put a prime sign on it. Let me simplify each of these terms. 5 minus 3 is 2, so we just have 3x squared. For the second fraction, this x has an implied 1. 3 is more than 1, so I do 3 minus 1 and get 2. But those two x's that don't cancel are in the denominator, so we have minus 2 over x squared. I'm going to write this, though, with a negative power so that I can use the power rule. So we have 3x squared minus 2x to the minus 2. Now I'm ready to differentiate both these terms at the same time using the power rule. So we get 6x is the derivative of the first term, and then minus, and then the derivative of the second term. This negative 2 will multiply to that negative 2, giving us a positive 4 coefficient. And the new power will drop to minus 3. And in the end, this is 6x plus 4 over x cubed. And the result we got here matches the result we got using the quotient rule. This is again a situation where I actually prefer this second method. But if I use the quotient rule, you should get the same result. Now, what made this second approach even possible was the fact that we had multiple terms in a numerator, but a single term in the denominator. For example, addition or subtraction of two fractions that have the same denominator, you can add or subtract those numerators and put it all over that same denominator. It's using this property of addition or subtraction of fractions backwards that allows me to take that b and split it up under the two terms of the numerator. We call this splitting the denominator. What would happen if we had the reciprocal of this fraction, such as b over a plus c? Be warned that you cannot split a numerator, so you would not say that this is equal to b over a plus b over c. Here's a simple counterexample. 1 over 1 plus 1 is not equal to 1 over 1 plus 1 over 1, because on the left side we have a half, on the right side we have 1 plus 1, or 2, not the same. So the second method is only possible because I was able to split the denominator. But if I take this function and do its reciprocal, put the x cubed in the numerator and the 3x to the 5th minus 2x in the denominator, I will no longer be able to algebraically simplify prior to differentiation, and I will be forced to use the quotient rule instead. We will see that on the next page. Moving on. Find each derivative below. So here it is. A single term in the numerator, but two terms in the denominator. There is no algebraic way to simplify this. I will be required to differentiate this function using the quotient rule. So think of the numerator as u, the denominator is v. So I'll get u prime v minus uv prime all over v squared. So in this case, we have the derivative of the numerator, which is 3x squared using the power rule, times the denominator, undifferentiated, minus the numerator, undifferentiated, which is x cubed, times the derivative of the denominator. Using the power rule, we get 15x to the 4th minus 2, and then all over the denominator squared. Now technically I'm done. This is the derivative, but we do want to simplify it to a more manageable form. So I'll begin by distributing. We have 3x squared times 3x to the 5th. That's 9, and then add the powers, x to the 7. 3x squared times negative 2x will be minus 6x cubed. Now over here, be careful, you distribute the negative with the x cubed. So negative x cubed times 15x to the 4th will be negative 15x to the 7th. And then negative x cubed times negative 2 gives me positive 2x cubed all over that same denominator. And now we can look for some similar terms. We have an x to the 7 term and another x to the 7 term, and then we have an x cubed term and another x cubed term. So combining the orange terms, we get negative 6x to the 7th, and then combining the green ones, we have minus 4x cubed all over that same denominator. Now we could stop here, or we could do some additional simplification because there are x's in every term. I'm going to factor a negative 2x cubed from the numerator, would leave me a positive 3x to the 4th plus a 2. And in this denominator, I'm going to take an x out, leaving 3x to the fourth minus 2, but that's all needs to be squared still. So that denominator would become x squared times 3x to the fourth minus 2, and that's being squared. The only reason I did any of this was I did anticipate some x's would be able to cancel. So as a final answer, I'm going to say negative 2x times 3x to the fourth plus 2 all over 3x to the fourth minus 2 squared. These terms do not cancel each other because they are not identical. So this is as far as we will simplify this. Now on that note, I could have factored some x's and simplified the original function to begin with before I ever applied the quotient rule. That likely would have led straight to this simplified version of our derivative. Okay, but moving on. Once again, we have a single term in the numerator, but two terms in the denominator, so I cannot split the numerator. So I have to use the quotient rule here. We have a numerator u and a denominator v. The quotient rule yields the derivative of the numerator. The derivative of square root of x is just 1 over 2 rad x, and then times the denominator, then minus the numerator times the derivative of the denominator, and the derivative of 3x plus 6 is just 3, and then all over the denominator squared. Applying the quotient rule here did produce a fraction in the context of a bigger fraction. So we have a complex fraction. I will multiply the top and bottom of this fraction overall by 2 radical x and distribute across the numerator, but leave the denominator factored. So imagine this 2 rad x multiplies. It'll multiply to the numerator here, canceling the 2 rad x in black. So my first term will just now be 3x plus 6 only. Now I'll multiply 2 rad x to this term. Well, the 2 and 3 will make 6, and the rad x times rad x will just make x. So we're going to have a minus 6x, and the numerator becomes very clean. The denominator will be this term and then this term, and I'm going to leave them factored. And I'll put the 2 rad x first. So in the end, this simplifies. We have 3x minus 6x. Those are similar. So we have the constant 6 and then minus a 3x all over a 2 rad x times a 3x plus 6 squared. Be careful you do not cancel these because they are not the same. And this is a good place to leave our answer. It's a non-complex fraction. Okay, moving on to the next page. Find each derivative below in 2 ways using the quotient rule for one of the methods. And once again, we see we have 3 derivatives in pairs. The first pair, I do see a fraction. We have x divided by 5. The fastest way to think about this is to think of 1/5 as a constant times x. And since it's a constant, I can factor it to the front and then simply differentiate the x that's next to it. And the derivative of x is just 1, so I simply get a 5th. This is a fast way to get this derivative. Let's go ahead and use the quotient rule where u is x and v is a 5. So the quotient rule says that we'll have the derivative of u, which is 1, times the denominator 5, minus the numerator x times the derivative of the denominator. But the derivative of 5 is 0. And this is all over the denominator squared. So I get 1 times 5, which is 5, and then minus 0. So we just have 5 in the numerator, but 25 in the denominator, or we can cancel some 5s. And in the end, I confirm that the derivative of x over 5 is simply 1/5. The quotient rule did not contradict the more simple way to approach this one problem. Okay, now how about 5 over x? One way to do this problem is to rewrite this as a power of x, 5x to the minus 1, and then differentiate that using the power rule. So the negative 1 will multiply to the 5, so we have negative 5, x to the, and our new power will be 1 less than negative 1, so negative 2. So in the end, I should get negative 5 over an x squared. But let's confirm this answer by employing the quotient rule. U will be the 5 and v will be the x this time. And the quotient rule gives us the derivative of u, the derivative of 5 is 0, times the denominator, minus the numerator, times the derivative of the denominator, and the derivative of x is just 1, all over the denominator squared. Of course, this term here is 0, so we just get minus 5 over x squared. The same answer we got before, and arguably just as easy. And let's do this third example. The way I would approach this is we have 1/5 times 1 over x. So I would pull the 1/5 and the 1 over x apart. The 1/5 is a constant. So I could ignore it for now and just differentiate 1 over x, which is x to the minus 1. So the 1/5 stays, and now I differentiate x to the minus 1 using the power rule, and we get negative x to the minus 2. So we have 1/5 times negative 1 over x squared, and in the end that gives me negative 1 over 5x squared. Okay, let's confirm this using the quotient rule where u is a 1 and v is a 5x. So the derivative of 1 is 0 times the denominator 5x minus the numerator 1 times the derivative of 5x, which is just 5, all over the denominator squared. Now make sure you put this 5x in parentheses and then square that. this product is 0, so we get negative 5 overall in the numerator. And in the denominator, as a reminder, when you have a product being raised to a power, that a power can affect both factors of the product. So 5x in parentheses being squared would give me 5 squared, or 25 times x squared. And of course, now I can simplify. We have negative 1 over 5x squared, confirming the answer we got above. Okay, these two rules, the product rule and quotient rule, will be used extensively for the remainder of this course. And this concludes our lesson on these two rules.